here, where that's Kipp, recently took a faculty position at the University of Tokyo, and is here to tell us about his work.
Yeah, so now I can finally tell you guys what I was doing this fall. The group meeting reports were sparse. I just had to say, well, I don't know, I've been on telecons. Yeah, so this is, people have been asking about, I have a rare example of a name that can be meaningfully written in Japanese. This started out more as a joke than anything else. So it's read, this is Kanon, this is the Japanese characters for Buddha, and then Kippu, which is a ticket. So it's Buddha ticket. But just before coming back here, I tried to pay my first internet bill. And it was a total disaster. And I discovered that Japanese has small numbers and capital numbers, just like we have small letters and capital letters. And my keyboard couldn't enter capital numbers. So I had to ask the secretary at the institute to help. And we finally got through the whole web page. And then the system would refuse to do an electronic fund transfer from a bank whose account holder's name is written in Latin letters. You have to have a Japanese name. So at that point, I was sad I hadn't opened my bank account with this name. So anyway, it's become a bit of a mess. Right, so all of the stuff that I'm going to present, you can now find online. The main result is available in this document. This is the date of the binary black hole merger that was observed 2015, September 14th, and this is the LIGO document control system. This is also available on arXiv and through PRL. We also have this thing called the LIGO Open Science Center, where you can download the data in question. There's also audio files that you can listen to. There's posters you can post around to advertise gravitational wave astronomy if you wish to. All sorts of things. It also has links to all of the other papers that are trickling out in association with this event. So the heart of the matter is this paper with a title that we weren't sure we would ever be able to put on a paper, the observation of gravitational waves from a binary black hole merger. We were basically expecting to have to write a paper entitled Evidence for Observation of Gravitational Waves from a Binary Black Hole Merger. But this signal that was seen in the data had such an extremely high signal-to-noise ratio that we were able to convince 1,000 people to put this strong a statement on the title of the paper. The event, this is, as I said, appears to be the merger of a pair of high stellar mass black holes. It was observed at about 9:50 UTC on September 14th, which is just a few tens of hours after the start of the observing run. So as soon as we turned on the detectors, basically almost immediately, binary black holes started coming out of it. The signal-to-noise ratio was extremely high, 24. This is high enough that you can hear it in the data, which is sort of unusual. And the false alarm rate is bounded to be something less than 1 in 200,000 years, and this is from 16 days of data. So the statistical significance of this is high enough to make this detection claim. The distance to the source is not clear. I'll talk more about that later. It appears to be somewhere at this range, 410 megaparsecs, with a fairly large uncertainty on it. That corresponds to a redshift of about 0.1, which means it's far enough out that we need to worry about whether we're talking about the masses of the source of the black holes at the source or here at Earth, because the gravitational waves have been redshifted appreciably in their transit through the universe. So the signal that has arrived here at Earth is at a lower frequency than it was emitted at. And that makes the masses appear to be heavier here at Earth, because you infer the masses from the frequency content of the data. So these are the inferred masses at the source, which means they include the uncertainty in the distance to the source. The black hole that remained after the merger is inferred to have this mass, 62 solar masses, and altogether it appears that 3 solar masses of energy was radiated during the collision. The peak luminosity works out to about 200 solar masses per second being radiated, which, and I don't remember exactly how the numbers came out on this, but I think that's something like 50 times the luminosity of all the stars in the visible universe for a brief period of time. So all of these plus minuses are the 90% credible intervals on these numbers. Okay, so a little bit of a history lesson of how we got to where we are. So in 1915, obviously, everyone knows, Albert Einstein publishes the Lorentz invariant theory of gravity, in which gravity appears as the dynamic curvature of space-time, and we call this today general relativity. In the very same journal issue, Karl Schwarzschild published the first solution to the GR field equations. Einstein famously thought the field equations might never be solved. They're nonlinear and extremely complicated, and this mathematician managed to pull it off right away. He did it while in the trenches of the First World War. He didn't survive the First World War. He died of a disease. He wasn't shot. But he was able to obtain the first solution of the field equations with all the shelling going on overhead, probably by candlelight or something. Anyway, it's kind of amazing, the achievement. Of course, he did it by using the standard trick that you teach undergrads in partial differential equations courses. You start by setting as many derivatives to 0 as you can to simplify the problem, which reduces it to a one-dimensional differential equation. And he was able to solve that ODE for the radial part of the solution. And at the time, it wasn't known what the solution described because it had some problems with it. And today, we know that it's the solution of a black hole. He had obtained the description of a black hole. So the black hole is actually one of it's the first object to be known in general relativity. So a year later, Albert Einstein published a wave solution in the weak field limit of GR. And by the 1960s, it had been decided that these waves were, in fact, a genuine phenomenon and not just a mathematical artifact. Joseph Weber began searching for evidence of these waves with resonant bars. His work has subsequently been discredited because he made claims of detections that were subsequently shown to be false. And he stuck to them solidly. But he's today looked at as having really opened the doors to other people exploring other ways to search for gravitational radiation. And so in the 60s and 70s, you also see the start of laser interferometers being used for gravitational wave searches. Probably the most famous one is the so-called Malibu interferometer that was built by Hughes Aircraft, by a researcher at Hughes Aircraft in the early 70s. And was, I believe, one of the most detailed descriptions of it was presented at a GR conference just over at the University of Waterloo in 1978. So by the 1990s, the LIGO project had gotten started. And in the early 2000s, we performed 6 observing runs, many of them jointly with other interferometers that have been constructed around the world, including GEO 600, Virgo, and Tama interferometer in Japan, as well as the resonant bar detectors that were still in operation during this time. There have, of course, also been other gravitational wave detection efforts, including pulsar timing and searches for evidence of gravitational waves in the polarization maps of the CMB. In 2015, in September, the Advanced LIGO Observatory began its first observing run. This was a rebuild of the interferometers using a higher power laser and new optics and more sophisticated suspension systems, which improved the sensitivity at low frequencies. And almost immediately, we detected evidence of a binary black hole merger, which took us until February of 2016 to publish. But that works out to 1916 plus 100 years. So we like to say it's the 100th anniversary of the prediction of gravitational waves when we were able to publish it. Okay, so a little bit about the behind the scenes of what was going on at the time. So early September 2015 was, we were still in what was called the engineering run. So the science data taking had not yet begun. People were going in each day to the observatories and tinkering with the control system software and tinkering with electronics. At the data analysis end, we were still adjusting details of the ranking statistics used to try to detect things in the data. So the detectors and the analysis software were both undergoing their final shakedown before the official start of science data collection, which was to occur that weekend. And early Monday morning at 9:50 UTC, so this was 4:50 in the morning local time at Livingston and 2:50 local time at LHO, a low latency burst search pipeline called Coherent Wave Burst registered a moderate significant candidate which appeared in time frequency plots to have the sort of chirping structure of the merger of a pair of black holes. So that candidate was uploaded to our event database with a latency of about 3 minutes, but that basically, well, triggered several days of confusion. So the thing was that there were 2 low latency compact object searches running at the same time, neither of which registered the event. What had happened was the compact objects group had chosen to restrict the scope of the online analyses to just low mass systems, so systems involving at least 1 neutron star, in the belief that these would be the only candidates of interest to people with electromagnetic telescopes to whom we were transmitting these alerts. The rest of the collaboration was not aware of this decision. And so the fact that a burst search was claiming to have found a pair of black holes and the purpose-built pipelines were saying there's nothing of significance in the data initially led to suspicion that this pipeline was broken somehow. Also, it was the middle of this engineering run, so people had been intending to come in those mornings and start tinkering with the observatories. It wasn't clear what condition the observatories were in, whether the data was good enough, whether perhaps there was something funny in the software that was maybe putting artificial signals into the data. So it took quite a while to sort out what was going on. Well, in hindsight, it looks like it was pretty quick. At the time, it seemed like it just dragged on forever. So Wednesday, September 16th, at 1700 UTC, the spokesperson for the LIGO Scientific Collaboration sent a manual email to the people with electromagnetic telescopes saying that this feature was present in the data and they should begin pointing their telescopes. The alert system that should have sent it out automatically had been turned off because it was still the engineering run period and we were not sending automatic alerts because people were screwing with the observatories. So it was determined that 16 days of coincidence data would be required for the compact object search pipelines to determine what the false alarm rate of this event was to the level required to make a detection claim, if that did turn out to be its significance. So we went ahead and collected that data. Of course, we've now collected several months of data, but all that has been published at this time is the contents of that 16-day period. The rest of the 01 first science run has not yet been published.
So that's the 5.1 signal?
Yeah. So we sat and waited for 16 days, and during that time, a second binary black hole merger was identified. Now this candidate's false alarm probability is very high. It's at the few percent level. It's about 2% false alarm probability. So 1 in 50 equivalent experiments are expected to yield something like this just by random chance. So it's not significant enough to be a detection claim on its own. But in the context, like in a world in which you believe you have built gravitational wave detectors and there are sufficient sources of sufficient brightness for you to be detecting gravitational waves regularly, then this is more correctly interpreted as a signal rather than a fluke outlier of the noise. And so it has a significant impact on the event rate estimates for black hole mergers. So this candidate was also observed Monday morning. In fact, it was observed 4 weeks and 4 minutes after the first one. So they came to be known as First Monday and Second Monday internally. Here's the time series for the observatories. So it's been downsampled to 2 kilohertz. The data is collected, I actually don't know what sample rate it's collected at anymore. I think it's maybe 32 kilohertz, but what the analysis pipelines are fed is sampled at 16,000 samples per second. This has been downsampled to 2,000 samples per second because the signals have a relatively low frequency, and so you don't need that many samples. And so, you can see the individual up-down spikes of each sample at 2,000 samples per second. What you're seeing is the gray is a band. Well, it's the whitened data. So the time series, the strain data from the antenna, has been passed through a linear filter that imparts a spectrum that exactly cancels the noise spectrum of the antennas. So what comes out of the filter is a good approximation of stationary white Gaussian noise. It's normalized so that it's unit variance, and this is what you see on the right-hand side. This is sigmas from the mean. So it's zero mean unit variance Gaussian random noise. The signals that are inferred to be present in the data are shown in cyan and blue. The cyan is the envelope of the posterior samples from the parameter estimation code. So what's happened is the codes that try to estimate the physical properties of the source are drawing mass parameters from the posterior distribution. And what's happened is all of the different samples that are drawn have been overlaid on top of each other. And the 90% sort of envelope from those samples has been indicated. So it's fairly tightly constrained. The cyan is basically, the whatever that is, color, purplish, is something similar, but using a wavelet denoising algorithm. So the cyan is imposing the constraint that what is in the data is a binary black hole merger as described by GR. The other is not. It's just based on a denoising of the data. So that's basically what it looks like. It really stands out. Now, of course, it's only in the whitened data. I should also point out that these little wiggly bits are the effect of the whitening filter on the signal. The GR does not predict that structure should be there. That's what happens when you take the waveform predicted by general relativity and run it through the whitening filter that has been applied to the data. So another way to sort of look at the significance of this event is a plot like this. So let me just back up one slide. So from something like this, what we do is we take the inner product of a waveform, a GR waveform, and the data, just treating each sample as a dimension of a high dimension vector. We take that inner product, and that inner product gives us what's called the matched filter signal to noise ratio. If you then subtract that signal out of the data, you're left with this gray residual, and you can compute a sum of square integral for that to get a measure of the magnitude of the residual. There are a lot of details in how you do that. You don't want to just sum up all the samples. You end up with a lot of noise. You need to sort of pick a few that are useful. So that it's not quite as simple as just a sum of square residuals, but conceptually that's basically what's going on. So that gives you two numbers, an inner product amplitude, or matched filter signal to noise, and then a square magnitude of the residuals on this axis. So the left plot is for the Hanford Observatory. The right plot is for the Livingston Observatory. This orange density plot up here shows the density of things that come out of the detector that are determined to be noise events. So things that fail coincidence between the two detectors. You see this distribution like this, and in Hanford you have a distribution like this. The red X indicates the location of the first Monday event in this parameter space, and the blue plus is the second Monday event in this parameter space. So the red X is well off the edge of this measured background. What you've got is this kind of ratty edge where the last few samples have been collected, and then there's just nothing. So the red is beyond any observed background in the antennas. There's simply no noise that looks anything like it, which makes it impossible to estimate its false alarm probability correctly. No, this is just comparing the antennas to template waveforms. And then, so this is the match filter SNR for the templates, and then the square magnitude of the residual. So signals are expected to be down here, and noise ends up. So noise has high residuals as the SNR increases, and signals should have lower residuals as this.
Probability isn't even taken into account that you saw it for antennas.
Right. Well, that's right. So the problem is we can't compute its false alarm. We don't know what this probability density looks like out here. You can extrapolate, but the collaboration doesn't like doing that. So what we did instead was adopt this modified noise model where the candidate itself was labeled as a sample of the noise. So we say, let's assume that this candidate. So normally, all of the things that are coincident between the detectors we put aside, and we say that those might not have been drawn from the noise population. All the things that fail coincidence, we believe have been drawn from the noise population, and they go into these probability densities. So you can modify by taking the stuff that you've set aside and call it all noise. And what happens is, so there's actually two PDFs. where they differ, there's this second color bar here, but you should imagine that this actually blends into the orange. And I think if you look really carefully, what you'd see is that the numbers actually match up at the interface. But basically, the point is that the distribution up here is exactly the same as far as you can tell, except there's now this little island of probability density down here, which is the candidate, which is the result of the candidate itself, as well as other things in its vicinity. So now it's sitting on a little island of probability. So you can now estimate a false alarm probability with that modified model. Of course, you don't believe this is noise, and so you don't believe that this little puddle of density is an accurate measurement of the distribution of noise events. So this is really a bound on the false alarm probability. It's not a good estimate of it. But that number comes out to be quite small. So treating the resulting false alarm probability as a bound, you get it's below 1.4 times 10 to the minus 11 in the 16-day experiment. So it's an extremely high significance event. There were two search pipelines, two independently developed compact object search pipelines that recover the event. They're just meaningless letters that you don't need to know the origin of. The left plot is from a pipeline identified as PyCBC. The right hand is from a plot from a pipeline identified as GST-Lau. The horizontal axes on both is a ranking statistic. So this is taking those SNR and chi-squared values and digesting them into a single measure of how good the candidate is. So to the right is more signal-like, and to the left is less signal-like. And this blue histogram in both cases tells you the expected number of events in various bins of this ranking statistic for the standard noise model. And this black one is for the modified noise model, in which the candidate is included in its own background. And you can take these two curves and use them to translate ranking statistic values into sort of statistical significance in units of sigmas. And what you find is that the GW 150914, so that's September 14th, 2015, is well beyond the 5.1 sigma level in both, regardless of the choice of noise model. So this one, I mean, like I said, you can extrapolate those probability densities beyond where they're measured, and that's what this curve is doing. And if you keep going, you end up with some ridiculously small number. Okay, so why was it important to have been doing low latency searches at the time? Well, it's basically how we know this candidate wasn't artificial. So what happened that Monday, instead of people going in and fiddling with the observatory because they knew there was something of significance in the data, the work for the day that was planned was canceled. And instead, people ran around and carefully documented the configuration of the interferometer. And something like 460 photos of equipment racks like this were taken. And they've subsequently been scanned by experts in each of these subsystems to confirm that each cable has been connected to the ports that it should be connected to. And in particular, the test input ports have nothing plugged into them. So this is where signals could be injected into the control system. The other thing that was done was holographic tamper-proof stickers were placed over the chassis edges. So the chassis were sealed, and they were then opened at the end of the run to confirm that the contents of each electronics rack were as they were intended to be. So of course, none of that work would have proceeded if we hadn't known that that thing was in the data until weeks later when the offline analyses proceeded. And it's not clear what the paper would have said. Of course, we would have published the event, but without this level of documentation for the condition of the interferometer at the time, the title might not have been Observation of Binary Black Hole Merger. A tremendous number of electromagnetic observations were performed following up on the event. So this is a posterior probability density for its location on the sky. It's huge. it spans something like 600 square degrees. The 90% confidence interval spans 600 square degrees. But these are pointings that have been done. And if you zoom in and you can see there's tons and tons and tons of little pointings that have been done all over the place. The sun and the moon interfered with some of the pointings in the northern hemisphere. But a lot of analysis of this candidate has been performed. So, okay, what can we say about this binary black hole merger? So we want to interpret this observation, and doing that requires that we understand what it is we're seeing. And if our assumptions are incorrect, then our interpretations will not be correct, right? So, so to identify the candidate, we use these template waveforms, and to infer its properties, we have used two different phenomenological waveform models, both of which have been calibrated to numerical relativity simulations. So as you might know, numerical relativity simulations of binary black hole mergers take a lot of CPU time, and so it's not possible to do an MCMC style parameter estimation analysis running numerical relativity simulations inside your MCMC code. So what we use are a small number of numerical relativity simulations, and from those construct phenomenological models that approximate them very well, but then can have arbitrary parameter values put in, so we can generate other waveforms very quickly. But these have uncertainties. They don't reproduce the numerical relativity simulations exactly, and it's not known how well they work where simulations have not been performed. So that's why it's important to have at least two of them. And then we basically use the differences between the two models as a surrogate for the uncertainty in the model. It's a little hand-wavy, but that's basically all we can do right now. The other advantage of having these phenomenological models is they have these more or less arbitrary parameters in them, which are set in order to make the model fit numerical relativity. But you can imagine just screwing with these parameters a bit, and now what you've got is a model that can simulate departures from general relativity. So we also look for evidence of that. So for the astrophysical implications of this observation, there's a paper that has this code, 1500262. And actually, not much can be concluded from the observation itself, astrophysically. Several previously unknown things are immediately established. First of all, that heavy stellar mass black holes exist at all, that they do form naturally in binaries, and that these binaries are tight enough to merge within the age of the universe. Those were all speculated to have been true, which is why we searched for these signals in the first place. But none of this was known to be true, unlike for the case of binary neutron stars, where we do know neutron stars exist, we know they occur in binaries, and we know those binaries are tight enough to merge within a Hubble time. We can't constrain the origin of this system. I'll talk more about that later, but we do not know at this time whether its properties suggest a recent origin with a prompt merger, or an early origin in a very long evolution timescale for the system. The Fermi satellite identified a possible gamma ray emission associated with the event. This is a 3 sigma accidental coincidence with the candidate. There was not necessarily any reason to believe the merger of a pair of black holes would be a significant source of gamma rays, which did not stop immediately a large collection of models for how you can get gamma rays from a pair of black holes merging. One of the suggestions that has come out is that this might not have been 2 black holes. It might have been a single collapsing star whose core fragmented into 2 collapsed centers rather than a single black hole. And the black hole merger actually occurred inside the envelope of a collapsing star. That's one of the suggestions. Anyway, you can come up with others if you wish. So here's the posterior probability density for the masses of the 2 component objects. So we apply a convention that M1 is the heavier of the 2. So this cut is the equal mass line, and we define the system to be on this side of the equal mass line. And this contour that is the better constrained direction that's the so-called chirp mass of the system, which is this combination of M1 and M2 that's better constrained. We're not able to constrain the individual masses very well, or at least not as well as we can constrain the direction along this contour. The red and the blue histograms here are the posterior PDFs obtained using these two different phenomenological waveform models. So you can see that they're relatively similar, but there are some significant differences in places. And then the black is the combination of the two, so taking the samples from both systems and just combining them into a single histogram. So you can get a sense of how uncertainties in the waveform model might impact the interpretation of the masses from this.
Have there been more of the quote real simulations run since to try and fill in this parameter?
Not since. So there has been some numerical simulations of this particular system. So Harold ran a simulation basically taking the maximum likelihood estimates for the system's parameters. And that was used for the movies that you've seen associated with the release. But there hasn't been a systematic study of the parameter space in this area, no. So this is the final sky map. The one I showed earlier was the one that was available at the time the alert was sent to the EM telescopes. And when more computer time was spent on it, it could be refined, and you can see that the probability mass in the northern hemisphere has shrunk substantially. So people wished they had spent more time focusing on the southern hemisphere. But as I said, it's still an enormous area of the sky. The 90% credible region is around 600 square degrees. So here is the posterior distribution for the distance to the source and the inclination of the binary system. So these two parameters are degenerate. If you see the system edge on, right down the axis of the orbit, then the intensity of the gravitational radiation is higher than if you are looking at the system edge on. Now, unlike many astronomical sources, the amplitude of the gravitational waves is exactly determined by the properties of the system. So the masses that were involved and the spins fix the amplitude of the gravitational wave. So by measuring the amplitude here at Earth, you can determine fairly exactly how far away the system was. But in this case, because we don't know the orbit inclination, we don't know the orientation that we were observing here on Earth, there's some uncertainty in the distance. So the posterior probability for the orbit inclination basically favors face on, but that's mostly a result of the math understanding that there's more space further away. And if we saw it face on, then we could have seen it at a larger distance, and there's more volume of space out there for the system to be located in than edge-on systems that are close by. So in a sense, it's just telling us what we would have expected for a first detection, which is that first detections are probably going to be face-on at far distance, and later, when we see when we have more sensitive detectors, we'll start to see edge-on systems. The way we would normally disentangle the orbit inclination is by measuring the polarization of the gravitational wave, but for this observing run, only the two LIGO detectors were operating, and they are very closely aligned to one another. A gravitational wave antenna is a lot like an electromagnetic antenna. It can only normally see a single polarization state of the wave field, and these two antennas are aligned. So for most of the sky, they're basically seeing the exact same polarization state. So the two LIGO antennas are not enough to disentangle the polarization. We don't know if it was linearly polarized or circularly polarized, and that would have told us whether we were seeing it edge on or face on. And so that would constrain the distance a lot if we knew more about the polarization of the signal.
So why is this plot not measured around 90 degrees? Is that from the little bit of polarization?
Yeah, it's yeah. There's a little bit of information. This is the posterior distribution for the spins of the two systems. The radius is the dimensionless, the magnitude of the dimensionless spin, and the angle around here is the angle from the orbit axis of the system. And in these coordinates, the prior probability distribution was uniform. So the structure that you see is what the data has told us about these properties of the system. In particular, the heavier mass of the two is almost certainly not maximally spinning, which is interesting. There's been some speculation that many black holes in nature will be near maximally spinning. So it appears certainly not to be. We're not really able to constrain the in-plane component of the spin, although it appears that the component, the Z component, is close to 0. And for the lighter of the two, less can be said about what spin it might have. But this is where you would learn about the origin of the system. So if the spins were aligned with the orbit axis, that might suggest a system that had undergone a very long, slow evolution in which spin-orbit couplings have caused all of the angular momentum vectors to align themselves. A prompt merger or a dynamical capture scenario where these two black holes had some sort of independent evolution and have recently been brought close together through interactions with other objects could result in the spins being just randomly aligned and all over the place. And there's not really enough information here to say which of these two scenarios this system has. Are they aligned or not aligned with the orbit axis? We need more signal-to-noise ratio, and it would also help to have additional detectors that are not aligned with the LIGO detectors, so we can see the other polarization components of the waves. And that would indicate whether we're seeing precession and so on. So for the final black hole that results after the merger, again, here's the dimensionless spin on the vertical axis and the mass of the system. So as I said, approximately 3 solar masses has been lost, and given the time that elapsed, the luminosity is estimated to be about 200 solar masses per second. So that works out to, at a distance of 1.3 billion light years, a flux density at Earth of 10 milliwatts per square meter, which is, for astronomical sources, an absurd power density. But of course, it was all in gravitational waves, and everything is transparent to these things. So you're mostly unaware of these tremendous explosions going off in the universe. So when the initial round of papers were published, one of the joint analyses with a non-gravitational wave observatory had been completed. It was the search for high-energy neutrinos using the Antares and IceCube detectors in association with this candidate. So it's a relatively straightforward search that simply looks for a neutrino within 500 seconds of the event. 3 neutrinos were identified, which is consistent with the background. So this is said to be a null result, and the whole thing can be seen here. Now, these detectors are searching for high-energy neutrinos in this energy range, 3 TeV to 100 PeV. So whether you believe anything could have produced neutrinos in this energy range is still something to be considered. However, if you imagine a 1 over E squared energy spectrum for neutrinos, then the null result in this energy range basically allows you to set an overall bound on the total flux of neutrinos that were released. And it comes out to something like this, less than 10 to the 52 to 10 to the 54 ergs was radiated isotropically in neutrinos. Now the gravitational wave energy emitted was 10 to the 54 ergs. So, and the maximum likelihood location for the source was deep in the southern sky. So this uncertainty comes mostly from not knowing the latitude at which the source was located on the sky. And then how the sensitivity of these detectors changes with latitude. But IceCube is more sensitive to things deep in the southern sky. And at the maximum likelihood direction for the source, you get bounds more like the lower end of this range. So if the source is where the posterior PDF sort of indicates it was, then the neutrino emission is less than 1% of the total emission of energy, which I think is interesting. Now, again, it depends on whether you believe the spectrum has no cutoff. But if these objects were not vacuum solutions of space-time, if this was some sort of previously undescribed exotic state of matter that had collided, you could imagine that radiating 200 solar masses per second in a short period of time, it would be hard not to get some sort of flash of neutrinos coming out as well. And again, now there might be some cutoff to the spectrum, but I think that this, I don't know, I feel that this is a nice indication that what collided was in fact vacuum space-time, not some sort of exotic state of matter. But I am not a neutrino physicist, so I don't know. Yeah.
Are there any theories that would have that neutrinos come before the gravitation?
No.
Because that's a symmetric coincidence.
Yeah, no, there's not. So, yeah, so for core collapse supernova, for example, the neutrinos and the gravitational waves are expected to be mostly simultaneous, because they both come from the core and they both precede the photons, but together they should be basically simultaneous. Yeah, and even at 1.3 billion light years, I mean, this energy, the neutrinos are traveling at c. So they're, this 500-second coincident window after 1.3 billion years is totally fine. Yeah, so we have tried to do some tests of general relativity with this candidate. Okay, I'm going to wrap this up pretty quick. So we have this waveform that's visible in the data. We have an in-spiral part, and then the merger of the black holes, and then the ring down of the final black hole. From the in-spiral portion of the waveform, you can infer the component masses that are spiraling in towards each other, and from the frequency of the ring down, you can infer the mass of the final black hole that remains, assuming in both cases general relativity to be correct. And you can try to infer a mass and spin for the black hole by analyzing those two parts of the waveform separately. So you put a sort of a cut in the data, and you put a posterior probability on the mass and spin using the in-spiral portion. So measuring the two component masses, and then using GR to predict what the final black hole mass and spin should be, or measuring the ring down and using GR to tell you what that means the mass and spin of the black hole is. So in both cases, you're assuming GR to be correct, but you're using different pieces of the data. And so it's an opportunity for GR to indicate some sort of internal inconsistency. And so these are the two posterior probability densities you get. This is from the ring down alone. You get this contour, and from the in-spiral alone, you get this contour, and the whole waveform together gives you this contour. So there is this region in which the posted spiral and in-spiral phases are consistent, and they are consistent. That region is consistent with what you see from the entire waveform combined. This does marginalize over calibration uncertainties in the detectors. So there are some phase errors in the data that are unknown, and amplitude errors that are unknown. And if you include models for those, that actually results in the two estimates being correlated with one another, even though the data is disjoint, because the frequency and phase evolution ends up being coupled through the calibration uncertainties. You get this well, you get correlations in these samples. So what you can do is you could draw from both distributions simultaneously and plot the fractional difference between the two estimates on these two axes. And so in this case, 0 indicates the GR case in which they agree with one another. And so that's this plus, and the maximum likelihood value is a little off, but the 90% credibility region solidly includes the GR case. But this is a little interesting. There's the maximum likelihood is off a little bit, and so while this might be a misunderstanding of the calibration errors in the antennas, or it anyway, it's something to explore with future observations. All right. So as I mentioned, we sort of lack the ability to directly constrain the field equations from these observations, but we do have these phenomenological models, and we can look for evidence that the parameters are not quite right. So this is one of them. So these are the parameters from one of these phenomenological models. This particular model is called the IMR phenom model, and it basically is a frequency domain stitching together of a bunch of little power law pieces to try to fit numerical relativity waveforms. And so each of these little power law pieces brings with it a few parameters. There's an overall amplitude, there's a phase, there's a slope, and so on. And so these are then these parameters, and they're mostly meaningless, but they've been organized from left to right, from the low frequency parts of the waveform to the high frequency parts of the waveform. So these correspond to the early in-spiral phase, and these correspond to the ring down and merger of the black hole. The red posterior is what you get if you allow that one parameter to vary on its own. And the cyan is the distribution, the posterior distribution you get if you allow all of the parameters to vary independently. So just looking at the red, it looks like there might be some tension with GR, because you see a lot of parameters that are outside the 90% credible region, or just on the edge of it. But if you allow all parameters to vary simultaneously, then you find that there's actually almost no information on these parameters at all in the data. These just huge, wide open posteriors. Except for up here, we get nice constraints, and they all agree with GR pretty well. The only one of these parameters that could have been constrained before the observation of GW 150914 is this early sort of phase of the post-Newtonian, the zero-order post-Newtonian phase term, and that comes from observation of the binary pulsar J0737-3039, and its constraint is much tighter than we can place on this parameter. It's this tiny little black region here. None of the others can be constrained by any other observations except this one.
Is it easy to understand why, when you let all the parameters vary, that lowest frequency one is still so unconstrained?
No, I don't. Maybe Prayush knows. When you allow all these parameters to vary, why is this cyan so big?
Oh, that's because we are lacking sufficient number of inspiral cycles in the signal that we get. Okay. Yeah, so it's from this map you can see what part of the signal you saw. And it means
You saw
the right hand block,
yeah.
the right hand position. Which means you saw the partition of
All right, we can put a constraint on the graviton mass. Now, if the graviton is not massless, then the GR gets modified by the addition of this Yukawa type correction. And in general, that alters the phase evolution of the merging black holes. And you could search for evidence of graviton mass by looking at the phase evolution. We actually don't do it that way. We look for evidence of dispersion in the propagation of the wave from the source to Earth. So we look for changing, basically evidence that the frequency components have arrived at the wrong times. So now this, I'm not really familiar with the constraints, but people would like to argue that our observation of GW 150914 provides the tightest bound on the propagation speed of gravity, or the dispersion of space-time. So you can parameterize this as in terms of the Compton wavelength of the gravitons. And in this parameterization, again, the double pulsar provides this constraint that the Compton wavelength has to be greater than about 10 to the 10 kilometers, and in this case, it has to be greater than 10 to the 13 kilometers. So we extend this by 3 orders of magnitude. But there are other observations that beat this by 9 orders of magnitude. People say that there are model assumptions involved in this, and this is a more direct observation. But again, I can't really comment on that. Okay, one of the things that I'm sort of interested in is this. The GR predicts that there are only 2 polarization states for gravitational waves. And as I said, the antennas are each sensitive to a single polarization state. The 2 LIGO antennas are aligned, so we have been unable to even determine what polarization this wave had, whether it was linear or circular. And we certainly cannot say whether there are more than 2 polarization states in the wave field. But if we had Virgo and the Kagra antennas operating, so they are both misaligned with the LIGO antennas and with each other. So that would then be enough antennas to determine whether there are 2 or 3 polarization states for the wave field. Yeah.
Why weren't the LIGO antennas made up orthogonal?
Why were they made? It was expected that they would be the only ones operating, and the goal was to make them sensitive to the same signals. So if one would see something, then the other would see it as well. And you could use the coincidence to establish significance. So the focus was more on designing them to provide good statistical significance for a detection rather than extracting the most science from the detection. Misaligned would have been probably better for that. Slightly, you don't want them to be misaligned so much that they actually see completely different regions of the sky. But so the beam pattern is also correlated with the orientation. So there are directions that they are blind to, and those are aligned for the LIGO ones. So yeah. All right. So really quickly, I know I'm at the hour. We did also observe a second event. As I said, the false alarm probability is very high, so the collaboration has been unable to call it a gravitational wave. It's been called a LIGO-Virgo transient, 151012, or trigger or something. I don't know. I can't remember what the T stands for. Its properties are actually extremely similar to the other one. The numbers look different, but if you reanalyze the data using only a template for one or the other, that template is able to recover the other very well with high significance. So as far as the detection pipeline goes, they're almost indistinguishable, although a full proper Bayesian parameter estimation does show that they have different physical properties. It's a lot quieter than the first. Its significance is lower. That's because its signal-to-noise ratio is lower, which means it's further away. So the Z is about 0.2. As I said, it has a significant impact on the estimated rate of merges. So the posterior estimate is that the data set we observed contains, now this is the median, but the maximum likelihood value for the posterior is 3. So 3 signals per experiment. So there's the 2 that we appear to have seen, the first GW150914, this one, and then there's likely a third one hidden in the data that cannot be disentangled from the noise events.
And by experiment, you mean the 16
The 16 days, yeah. Yeah. This was work that Heather was heavily involved in, so you can ask her all about the details of this posterior estimate. So you can translate that into a posterior probability that each of the candidates belongs to the signal population. So for the GST-Lau pipeline, on the horizontal axis is the ranking statistic. GW150914 is at 77, so it's way over here, not shown. And it's the probability that it's a signal is close to 100%. This is the second candidate. The third candidate is already down at 30% probability that it's a signal. So the noise hypothesis is already favored. And then all the rest of the noise hypothesis is favored even more. So we can't tell which is a signal, but the evidence is that there's at least one other signal present in the data. This is just another way to show this. So the 2 search pipelines, the GST-Lau pipeline was measured to have a 60% higher volume times time sensitivity than the PyCBC pipeline. But if you do this signal count estimate, you find evidence of 60% more signals in the data for the GST-Lau pipeline. The result is that the rate in candidates or black hole mergers per cubic gigaparsec per year ends up being almost identical for the 2 pipelines. So the dashed is the GST-Lau pipeline, and the solid is the PyCBC pipeline. So they're very consistent with each other. The green is what you would get if only the first candidate, the first Monday event was in the data. The red is what you get if only the second Monday is in the data, and the blue is if both are present. So you can see that the first Monday is much more to the left. The math would prefer to interpret that, if it was the only thing in the data, as a fluke outlier. It's not consistent with a population. It seems to be just a random chance. You just got lucky and something loud happened while your detector was going. With the second Monday event, it now looks like a consistent population that's present in the data. And so even though that second Monday event is not very significant, suddenly the analysis indicates that what's happening is you're seeing a population of binary black hole mergers, not just a fluke outlier. There's actually a whole population present. And so in addition to the 2 that you can point to, there's probably another one in the data as well that you can't point to. So it actually increases the event rate estimate by a factor of 3, even though it's just one extra event.
So you didn't, the 16 days had nothing to do with waiting for the next event?
No, it was to wait to collect enough background to estimate the significance of the first. And then during that time, we got the second one. Yeah. All right, I'll just skip over that. So prospects for future observations. If you take that event rate, here's 01, and you imagine that we surveyed this sort of nominal volume times time, and you scale that by the volume times time you expect the second and third science runs to survey based on estimates of the improved sensitivity of the detectors, then you can just scale up the number of signals that you expect will be detected in these science runs. And so you have this range of uncertainties in the signal count and this range of uncertainty in what sensitivity will be achieved. So at the bottom end of things, you're looking at a few detections in O2, all the way up to many tens. And then the third science run, possibly as low as 10, and up to the many hundreds of detections in this science run that's coming up. So what happens is you can begin to anticipate being able to do tests of GR that require very large numbers of samples to look at, this is not a situation we were expecting to be in probably for decades. So we've gotten quite lucky with this. Anyway, so just a few personal observations. I've been in this collaboration since the author list fit on a single page. And we've always known that LIGO was built to detect binary neutron stars. Those are the only sources we knew from independent observations exist. And the thing about binary neutron stars is the merger of the stars occurs at such a high frequency that the detectors can't observe the waves from the merger itself. That they're hidden in what's called the laser shot noise. So this is high frequency noise, the photon counting statistics from the laser. We were also expecting the first detection to be marginal, right? As we improved the sensitivity of the detectors, eventually something would start to point up out of the noise, and what would initially be evidence for some statistically anomalous excess of events would over time be turned into a population. So what we were expecting the first detection to look like would be a marginal significance binary neutron star. We can't test general relativity from these things. All you can see is the early in-spiral phase, where we already know GR is correct from the Hulse-Taylor pulsar. And it would only be a marginally significant detection. So we weren't expecting to be able to learn much more from a first detection than just what can be inferred from its existence at all. So whatever you can do by counting binary neutron stars, that's all you'd be able to learn. But as you can see, all kinds of things have come out of this. It's been a high signal-to-noise ratio binary black hole merger. We can see the entire evolution of the space-time from the merger of the black holes down into the ring down of the final remnant. And all kinds of tests have been possible with this short little 300 millisecond chunk of data. So it's really quite remarkable. So general relativity has been tested in the strong field regime for the first time. All sorts of things have come out of this. It's been really amazing. So things I haven't talked about. I haven't mentioned anything about the implications of the BBH merger rate on the spectrum of the stochastic gravitational wave background. I haven't talked at all about the burst search efforts that actually identified the thing in the first place. I have not talked much about the instruments or the rest of 01. This was just the first 16 days. Now, it's the first 16 coincident days. There's only about another 16 more. But it doesn't take much imagination to do the extrapolation and see that there's a lot of interesting data, and O2 starts later this summer. So if gravitational wave astronomy has begun, it's fun. Thank you very much.
without even using match filter.
It was using match filter. Yeah. The burst search did not identify the second candidate. So the second candidate, so the second Monday event was not sent as an alert to electromagnetic telescopes. There hasn't really been any follow-up of it because it was only identified. So at the time, we still were not running low latency compact object searches that covered that mass range. And so it was only identified after the fact with the offline analyses. It wasn't identified in real time.
So match filter has been run and there are no other events.
In that 16 days, that's yes. Yeah.
So it's not a population, it's just
Yeah, that's the it's consistent with the tail end of a population because the yeah. The third one is inferred to exist. It's not you can't point to a third candidate in the data. It's inferred from the rate posterior to be present, but not it's not identified specifically.
Other questions?
Can you put, given that as the mass gets smaller, you have to move further in to see the same object. If you fix all the parameters of the merger except for the mass, can you put meaningful limits on the dependence of the rate on mass?
Yes, I skipped over that slide. So this is. So there's, unfortunately, those two, well, unfortunately, I don't know, it depends on your perspective. The two events are very similar to each other, which just seems to point to a population of 30 solar mass black holes, lots of them. So then the question is, what is the mass distribution of black holes? Are they just all 30 solar mass black holes, or is there like a distribution? So we don't, a paper trying to infer a mass distribution from these two. Yeah, but it's actually in the works, so it'll come out soon. But what we can do is ask, how sensitive is the rate estimate to the mass distribution you believe to be present? Because what comes out of the search pipeline is this whole population of candidates. They're all consistent with noise, except for these two. But you can, so it's by looking at all of them as a whole that you decide there's actually a third one probably in there somewhere. But doing that requires you to put in as a prior your belief about what distribution the masses of compact object mergers are. So for example, if you say, I believe compact object mergers do not have masses above 3 solar masses, and you put that in, then these all get discarded just on principle, because the ranking statistic says this is not a gravitational wave. You've told me what they look like. These don't look like what you're looking for. So the rate is, so you have to actually put in a prior that says these things can be gravitational waves. And so there's 3 choices that people have tested. There's this so-called flat, well, so there are curves here. There's blue, green, and red. So flat, reference, and power law. Flat is uniform in the logs of the individual masses, so they're uniformly distributed logarithmically between some upper and lower bound. I can't remember what they are. I think it's like 1 and 100 or something. And the aligned spins are distributed uniformly. The power law distribution just takes the salpeter IMF and extends it all the way up to tens of solar masses for black holes, and then says that the ratio, so that's for the heavier object. So M1 is distributed this way, and M2 is distributed such that this ratio is uniform. And then this reference one, this is where you assume that all black holes look exactly like either this one or this one. So you put delta functions on those 2 parameters. So again, the 2 pipelines, you get very similar posteriors from the 2 pipelines candidates. The reference one, so you assume a delta function on the 2 observed sources, or this power law one. For the GST-LEL pipeline, those 2 posteriors come out very similar to each other. For the PyCBC, they're a little more different. But it's really only this flat one that shows any sensitivity in the rate estimates. Anyway, so this is put forward as arguing that the rate estimate is relatively insensitive to what distribution of masses you believe black holes have, because the peaks move by not much more than the width of the distribution. So, but with more detections, then you expect these to narrow up. And, yeah.
Okay, well, maybe we should take further questions upstairs for coffee and cookies. But before we go, we'll be thinking about dinner tonight. Welcome. Let me know if you want to join. I'll send an email out.